So we've learned about permutations and combinations from the perspective of arrangements of items or objects or people, etc., in a line. But you also might come across scenarios where you're thinking about arrangements relative to not a line, but a circle. So, for example, what if the question was, how many different ways can we sit 4 people around a circular table and when there's 4 seats? Okay, so you'll first ask the question. But like you're saying, order matters, right? So that's the whole idea. We could put Tim here and Philip here, or we could switch them. And that'd be another arrangement, right? So it's tempting to say, okay, well, what about 4 factorial? That's what we would say if the number of different ways to arrange 4 people in a line, we would say 4 factorial, right? Well, the only issue in this case is that, so if we've got 4 people, Tim, Philip, Kate, Sally, okay, if we do like this, Tim, Sally, like this, okay? So that's one arrangement, but we don't want to count if all we do is just rotate everybody. Well, that's the same arrangement. It's just a matter of perspective and how you're looking at the table. So we don't want to count this, right? All we do is just rotate everybody over once. That's the same arrangement. So to fix this, we want to use the division rule. And it's simple to see how we need to apply the division rule. Okay, so what's happening is, if we think about the multiplication of 4 factorial, if you do 4 factorial, then for every arrangement, so if we have, okay, Tim, Philip, Kate, Sally, okay, so we take a snapshot of this arrangement, okay? Now, you can think about what you then do is you pause that arrangement and you also count. You shift them over once, twice, 3 times. So for every arrangement, you're adding 3 more. So let me try and illustrate this from the perspective of the event diagram. So you've got the event 1 is what we're looking for. The number of arrangements that doesn't count, just a shifted version of the same arrangement. Okay, that's what we're looking for. Event 2 is what we're trying to figure out what we need to divide by. So, okay, but what are we trying to divide by? It's something to do with the fact that if for every given arrangement, so these are connected, we're going to multiply these. For every given arrangement that we have in the count that we're looking for, okay, so we've got, let's say you have this arrangement here. It's like we're pausing that arrangement and saying, okay, this arrangement here includes 1, 2, 3, 4 circular rotations. Then we do another arrangement. We say, okay, this is Kate, this is Tim, this is Philip, this is Sally. Okay, that's another one of these M arrangements that doesn't include the rotations. And then we're multiplying it by what? Well, it's going to be by 4, not 3 by 4, because we're pausing here and saying, okay, we want to count. We've got 1, 2, 3, 4. There's 4 ways you can just rotate the table and have the same arrangement just from a different perspective all the way till you get back to the original perspective, right? For each one of these arrangements, that's a part of the count that we're looking for. So it doesn't include the rotations. If you want to get 4 factorial, you're pausing here and saying, okay, how many different rotations are associated with this arrangement? There's 4. For each one of them, there's 4, right? You want to take the number that we're looking for and multiply it by 4, because each unique arrangement that doesn't include rotations, if you want to incorporate the rotations, there's going to be 4 for each of those. You start here, then you shift over here, that's 1, shift over again, 2, shift over again, that's 3, and then you're back to 4. You started at 1. 1, 2, 3, 4. So what we want to do is we want to divide 4 factorial by 4. And the result is 3 factorial. Okay, so now that shows you how to apply the division rule for this circular arrangement case. So with that, you have everything you need to solve any kind of circular arrangement problem. So like, okay, if we were picking from a group of, let's see, so picking from a group of 10 people to sit around a table of 6, where order matters. Okay, well, this is easy. We're just going to say 10 pick 6, right? Kind of thinking about how these are in a line. That would be 10 P6. Okay, but we need to divide out all the different ways you can rotate the table and get the same arrangement. That's 6. Not 6 factorial, just 6. Because included within each one of these arrangements, if we think about the number that we're looking for, which is the number of arrangements not including the rotations, what that is you're taking that number that we're looking for and multiplying each one of those events by 6. Because each one of those events, you can pause and rotate the table 6 times. So we want to divide out 6, and that's it. So this would be, let's see, 10 factorial over 4 factorial times 6. So 10 times 9 times 8 times 5 times 4 factorial. So 10 times 9 times 8 times 7 times 5, like that. Okay, now, what about if this was a combinations problem? We're saying order doesn't matter, and we have a 6 people around this table. What are the different number of combinations we can seat people around the table, choosing from a group of 10 people? This is where you're going to really have to build your critical thinking skills when it comes to counting problems. Okay, so you might be thinking 10 choose 6 divided by 6. Okay, but we actually don't need the 6. It's just going to be 10 choose 6. And why is that? Because, okay, if we think about this from the perspective of a line, arranging these people in a line, so we know that with 10 choose 6, it's like this could be Philip, Kate, Tim, John, Richard, Alex. Okay, but 10 choose 6, the whole idea is we're counting, so we could leave, as long as we replace one of these people with someone else, that's a new count. So Philip, Richard, Kate, Logan, John, Alex. That's another count. The whole 10 choose 6, the idea is you would never see, when it comes to lining these people up in a line, you would never see 2 pictures that have the exact same group of people, no matter how they're ordered. You would never find 2 pictures where you see these 6 people in that same picture at the same time. Yes, you'll see John more than once. You'll see all these people more than once, but never with the same group of 5 people. That's the whole idea. Okay? So, but with that then, if we think about what we were, for the case of the permutations where order mattered, when you think about what we were trying to divide out because of the rotations, well, all of those rotations, it was the same group of people in the picture, right? But that did matter in terms of permutations, because in that case, it was like, so, okay, PKTJRA, now we could do what we were, with a rotation, what was happening is that it would turn into A, P, K, T, J, R, which from a linear perspective, you want to count this. But from a circular perspective, you just rotated the table, right? I could do another rotation. It would be what? So R, A, P, K, T, J. There's another rotation. But these are the same group of people. Anytime you do a rotation, it's the same group of people. Combinations already divide that out anyway. So the rotation issue doesn't come into play when it comes to a combination in this case. The answer here is just 10 choose 6.